numerical integration. So we learned before that to estimate the area under the curve, we divide the area under the curve into small interval, right? We divide the area into rectangle in which we can calculate the area, and we then add them together, and you learn to use the left point estimate or the right point estimation. So let's recall what that would look like. So given a function f of x, and we want to find the area in the interval from a to b, we then divide this interval into small area. And let's say I use 4 approximation rectangle here. And if you use the left end point, then we estimate the area underneath this curve by calculating this area here. And we add them up. So the area 1, area 2, area 3, and area 4. If you are using the right hand side estimate, then we use the left end point for our estimation. Again, here we have the interval from a to b, and f of x is continuous in this interval. And then we divide this, let's make say 4 interval. And if you want to use the right end point, then we calculate the area 1, area 2, area 3, and area 4. So you noted that we have an over and under estimate. So if we are go ahead and trying to see if we use the midpoint of the estimation instead, we will get a closer estimation, the closer value to the actual area under the curve. So let's go ahead and take a look at the midpoint rule. Assume that f of x is continuous on the interval AB, and let n be a positive integer and delta x equal b minus a over n. If the interval AB is divided into n subinterval, each of length delta x, and small m sub I is the midpoint of the ith subintervals, then the area under the curve is the total of the area that represent underneath this curve calculated by the midpoint. So here, if you look at the area number 1, this area is m1 f of m sub 1, that's the height of that rectangle, times delta x, right? A2 equal f of m2 times delta x. So note that here it seems like we have a better approximation. It seems like we have a better approximation of the area because this rectangle is closer to the curve. Now, again, similar with the using the left point or the right point to estimate it, the total area underneath this curve is the limit as we let n go to infinity of the integral from a to b. The limit at n go to infinity of m of this total area m sub n here, and that is the same as the integral from a to b of f of x dx. Now let's take a look at the first example. Use the midpoint rule with m equals 4 to estimate the value of the interval, then compare the result with the actual value of this integral. Okay, so if m sub 4 would mean n is equal 4. So here we know that n is equal 4. So next thing we will do is to calculate delta x. Delta x is 2 minus 0 divided by 4. That is 0.2 5, right? And so let's find the dou value m sub I that we are looking for. So here is our interval from 0 to 2. If delta equal 0.5, then each of this point is 0.5. This is 1.5. Then the midpoint we are using is 0.25, 0.75, 1.25, and 1.75. So these are the collection of points that we be using of the x value. Okay. So m sub 4, well, m sub 4 is equal to delta x, that is 0.5, times f of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75. So the estimate area here is equal to 3.875. Let's go ahead and compare this value to the actual integral. Well, the integral from 0 to 2, the x to the third dx, is equal to 1/4 x to the 4th. Evaluate from 0 to 2. This is 1/4 times 2 to the 4. And this is 16/4 equal 4. So the midpoint area make the pretty close estimation, right? Another rule that we want to talk about is, well, trapezoid rule. So how does trapezoid rule work? So assume that f of x is the continuous function on the interval a to b. Let n be the positive integer, and delta x equal b minus a divided by n. Let ab be divided into n subinterval and each of length delta x, with the endpoint at x naught, x1 to x sub n. Okay, so let's calculate the actual area here. And here we have here we use the 4 subinterval, and let's see what this look like and why we come up with that formula. You remember what is the formula for the area of the trapezoid? The area of trapezoid equal 1/2 the height times the sum of the two base. Yep. So let's make this A1, A2, A3, A4. So here we have this trapezoid. So the area 1 is equal to 1/2 times the height. The height of this trapezoid is the distance delta x. Times delta x. A will be f of x naught. B is f of x1. Yeah. The area 2 equal 1/2 delta x, f of x1 plus f of x2. The area 3 equal 1/2 delta x times f of x2 plus f of x3. Area 4 equal 1/2 delta x, f of x3 plus f of x4. So let's go ahead and total up this area. Then the total area equal, we factor out 1/2 delta x, and we add up everything in between. Was f of x naught plus f of x1 plus f of x1 make 2f of x1, 2f of x2, 2f of x3 plus f of x4. So you can see the pattern here. If you have nth interval then add the area from a sub 1 to a sub n, then t sub n equal 1/2 delta x plus f of 0 plus 2f of x1 plus 2f of x2, so on and so forth to plus 2f of xn minus 1 plus f of xn. Okay, then the area is just the interval, then the limit at n approaches infinity, as n go to infinity, equal to the integral from a to b of f of x dx. Use trapezoid rule to estimate the value of the integral for using 4 subinterval for the integral from 0 to 2 of x to the third dx. Okay. Let's first find delta x. Well, delta x we found earlier in the previous problem is 1/2. Okay, and let's find our endpoint. Well, this would be starting at 0. The next one will be 0.5, 1, 1.5, and 2. So using the trapezoid rule, t sub 4 will be equal 1/2 times delta x. That's 1/2 times f of 0 plus f of 0.5 plus 2f of 0.5 plus 2f of 1 plus 2f of 1.5 plus f of 2. And we go ahead and put this into our calculator, in which we get 4.25. And so here you see that we have an overestimate. So since I said we have an overestimate in this problem and we have an underestimate in the previous one, so let's talk about how much overestimate and underestimate that we are looking here. We are talking about the absolute and relative error. If b is our estimate of some quality having an actual value of a, then the absolute error is given by absolute value of a minus b. The relative error is the error as the percentage of the absolute value and is given by the absolute value of a minus b divided by a multiplied by 100%. So let's calculate the absolute and relative error in the estimate of 0.2, of the integral of 0 to 2 of x to the third dx, using both the midpoint rule and the trapezoid rule. So let's talk about the midpoint first. We know that the actual value here is equal to 4, and the estimate value was 3.875. Okay, so then the absolute error is equal to a minus b. That is the absolute value of 4 minus 3.875, and that is 0.125. And the relative error is equal to absolute value of a minus b divided by a times 100%. And that will give us 31.25%. So the error is about 31.25%. So if you look at the trapezoid, again, the actual value is 4. The estimate was 4.25. So then the absolute error is equal to 0.25, and then the relative error is called absolute value. The 4 minus 0.25, excuse me, minus 4.25 divided by 4 multiplied with 100, and that is absolute value of negative 0.0625 multiplied with 100, and that is 6.25%. There's a mistake here. The relative error for the midpoint is 3.125%.